Hello all, I'm Somnath Sengupta and I'm going to talk about the basics of sensors and actuators. So sensors and actuators are present everywhere and in fact they are also present in our bodies. So they provide a mechanism to implement the control system that our bodies are. So let us take the example of our eyes. The eyes detect light, then the ears they detect sound, our tongue they taste different food, then our nose they smell, that's again a sense, then our palms of our hand they sense the pressure and temperature, and they give feedback to the brain. The brain processes it, processes these signals, and based on which it acts by giving some signals, let's say to the muscles, for example, in order to, let's say, lift an object. So it gives a signal to the muscle which act as actuators, and they deliver some motion. Okay, and yeah, so that's how this loop of sensors, processing, and actuation take place in our human body. Now these sensors, as I mentioned, they are quite sensors and actuators are quite important, and because they are everywhere and not just in our bodies, as I said earlier. They are present in automobiles, aeroplanes, cellular phones, radios, chemical plants, industrial plants, in plenty of domestic equipments. They're everywhere, and they are very important. Now, coming to sensors, they provide the window through which a microprocessor or an intelligent system can see what is happening in the real world. So, in order to do some crucial control operations, it is very essential to understand what is happening outside the world and what is happening in the real world. So, it has to get the information before it decides and acts on certain entities. So this information is provided by the sensors. So in order to act, the actuators play the role of delivering the action. Right? So the actuators they trigger some action based on the command received from the computer, or the, you can say, the microprocessor or the microcontroller, and based on that action some job gets done. So some actuation happens, some activity happens, the intended activity happens, and through this we can confidently say that without the use of sensors and actuators there would be no automation. Okay, so these are some of the applications. On the left hand side you see sensors and actuators play a huge role in different applications in our, not just day-to-day life in our domestic use, but in the industrial in the industrial organizations as well. So let it be automotive or consumer electronics or aerospace or information technology or robotics, uh, biomedical engineering, you name it. Sensors and actuators have a huge role to play, and they have been playing for several decades, and they are advancing further with time. Some of the popular sensors are accelerometers, then you have the gas sensors, then you have the pressure sensors. Then coming to actuators, we can have a micro mirror switch, or we can have a motor. So they do the actuation job. And there are thousands of others. So these are just to name a few. Now, sensors and actuators are typically part of a computer-oriented process control system. Right? So they form the interface between the real world and the computer system, and they are very crucial in forming the closed loop system. Right? So to implement process control, the computer must collect data and transmit signals to the production process. So let's say there is a process in control system literature, it's called the plant, let's say. So that has to be, the plant can be a washing machine, it can be an automotive system, or it can be air conditioning system. So it has to be controlled, right? In order to control, we have to sense some information from it, and then based on the processing part, based on the processing, will actuate some action. So components required to implement the interface are sensors and actuators, and then in order to process them, in order to interface with these sensors and actuators, which will be typically outside the computing hardware or the system or the computer, the ADCs and DACs will play a big role in interfacing with the sensors and actuators. Now, then further, we can also have these IO devices for discrete data. So I'll just be coming to that in a moment. So these sensors, they are of different types, right? They can be of continuous or discrete type. So if, let's say if it is just the sensor is just trying to monitor the status of a switch, so it will just sense whether it is high or low. So that will be fed to the IO device of the intelligence system or the computer or the processing hardware. Similarly, if it is an analog system, the computing hardware or the computer understands only binary values, right? It's ones and zeros. So they have to be converted from the continuous analog systems to the corresponding digitals, for which the ADCs will come into picture. The ADCs will convert the analog values to digital values. Similarly, if the actuators expect to receive analog value or an analog commands from the processor, then the processor will convert its digital values to analog values and feed it to the actuators, so that the actuator can take action based on the command. It can so happen that the actuators can only receive discrete values. So in that case, the IO devices can be helpful. So no need of digital to analog conversion. Similarly, for the sensors also, if the sensor is very simple, they can be just directly fed into the directly to the IO devices of the microcontroller or the processing hardware, which will directly process without going through the ADCs. So this is a pictorial description of the computer process control system, and rather the block diagram version. And it's all about controlling the plant. So in order to control the plant, the actuations will give the actuation the actuation activity, but not before they sense. So the sensing, the information comes from the sensor. So based on the variables, let's say this is a vehicle, so it will sense things like the speed, or maybe if it is just an air conditioner, the sensing, the variable, the variable to be sensed will be the temperature, right? And so based on, but the computer controller can understand, let's say, only binary values, right? So in that case, if the sensor generates only analog values, so they have to be converted from analog to digital and then fed to the computer control device. Similarly, the actuator will also take in the values from the computer based on the whether it's analog or digital, and then based on the activity of the actuator, the corresponding transformation process uh, will be exhibited, and then that exhibit will be reflected in the value of the sensor, and this will go on and on continuously. Now coming to sensors, a sensor is a transducer that converts a physical stimulus from one form into more useful form to measure the stimulus. Right? So there are two different categories we can always categorize. So they can sense, the sensors can sense analog quantities such as pressure or sound, light, or temperature or touch. But they can also, as I mentioned earlier, that they can also measure binary quantities, right? So whether, as I said, that whether a switch status, whether the switch has turned on or off, so they can sense that status of the switch. They can also take pulsed values from pulse counters, right? So continuously, suppose there is a device, let's say encoder, it is continuous based on the motion of a motor, it is continuously generating some pulses, high and low pulses. So it will count the number of pulses, and then it will come to some conclusion about the speed of the device, right? So this is this is some about sensor. There can be other sensors as well. There can be, as I mentioned, temperature sensor, RFID, gyroscope, vision sensors, compass, tilt, acceleration, right? Now let us go a little bit more deep about the sensors, and then how they function internally in a generalized manner. So here we can have all kinds of sensors. Let's say they can take the example of a temperature sensor, and then this sensor interacts with the outside world because it is supposed to, and the sensor the temperature affects the resistance of the sensor, which results in a corresponding change in current flowing through that, which again results in the voltage change. And this voltage has to be again adjusted in such a way that it can be fed to a device which understands the level of voltage, the level of voltage. That is, let's say the device operates from 0 to 5 volt. So it has to be fed a voltage which varies only between 0 to 5 volt, not higher, or it cannot surpass 0 volt also. It cannot be negative volt also. So that may damage the device. So in that case, we can be assured that this is safe for the device. So it might so happen that this device may not be just a computer. It can be just a display device also. But these are the basic steps of getting a stimulus and realizing the output signal, which can be used as an usable information. So these are some of the commonly measured quantities. So we have that the sensors measure. Right? So there are different. They can be under different groups. They can be mechanical type of sensors, or thermal sensors, electrical sensors, optical, biological, acoustic, or even magnetic sensors. And under each of the type, they can be a variety of different sensors for measuring variety of parameters like position or displacement, the velocity. So typically they can be using LVDT or potentiometer. Then you can have strain gauges or torque sensors. For thermal, we can have temperature sensors. For magnetic, we can have magnetic field or flux sensors. So mind you that the same sensor cannot measure all these quantities. They are dedicated unique sensors for measuring each of these quantities. Okay. So this is just a very simple representation of the transfer function of a sensor. So the output of the sensor is just a function of the stimulus, and the output can be, for very simple cases, just can be say high or low, or 1 or 0, to indicate that something is occurring or not. It can also be a very linear function. Again, this is a very simple representation of the output of a sensor, and the C is the output value at some stimulus value of 0, and it can be just proportional to some input stimulus. So, or it can be some other complex function of the stimulus. Okay, so these are some of the definitions which are very important, specifically when you are looking at some data sheet of a sensor. Suppose you're trying to figure out which is the best sensor, and is it according to your needs. So there are different attributes of a sensor, or different characteristics of the sensor which tell you how the sensor performs. So through these attributes, you can have some idea about the performance of the sensor, and then uh, you can focus on what kind of sensor you really need. So let us come to uniformity. It signifies a type of systematic error that refers to the consistency of a measured variable, either in spatial distribution or compared to another sensor taking the same measurement. So let's say that 10 sensors are there, and they are measuring the same speed. So there should be uniformity among these sensors. So all the sensors should report the same output value. Right? So these should not be different among the different sensors. I mean, repeatability. So it is similar to uniformity, but it is with respect to itself, that today you measured some temperature. After let's say 100 days, if you measure the same temperature, you should get the same output value of the sensor. Okay, so yeah, so it is the ability of a sensor to provide the same result under the same circumstance. Similarly, the accuracy, it is just the difference between the measured and true value. So basically, you try to benchmark. There are some standard values and then or expected values. So based on the measurement, you just compare with the standard value and how different it is. So it's quite used in the during the calibration, and then you compare with the reference and say what is the discrepancy between the measured by the correct sensor and measured by the uh, by the test sensor that you're testing. Then comes the parameter of sensitivity. So again, these are all performance parameters. I hope you realize this. The ratio of the magnitude of the response to the magnitude of the quantity measured. Right, so it's like a transfer function kind of thing. So we have seen that in the transfer. So that, or rather, per unit change in input, what is the output? Right, that is the typical definition of sensitivity. And for the sensor, again, this holds true. This, and it is also, we can also characterize it by saying that it is the smallest absolute amount of change that can be detected by a measurement. So we can present it in that way as well. Then comes the stability. So it refers to the degree to which the sensor characteristics remain constant over time. It doesn't drift, right? Because typically due to aging, or due to maybe accumulation of some um, some unwanted particles or something, so the characteristics change. So that's if so that is not a desired thing. So we are trying to understand that how in order to characterize the performance in terms of stability, we say that how it how much has it drifted from its initial value. Then comes the resolution. So it is the ratio between the maximum signal measured to the smallest part that can be resolved. So usually in conjunction with the A to D converter, that is the analog to digital converter. That rather than analog to digital, we also say that each bit signifies how much of millivolts or volts. Typically, it's millivolts. So it is the smallest. So it signifies the smallest possible measurement, and that is, again, as I mentioned, the ratio between the maximum and the smallest that can be resolved. So these are all important for choosing the right sensor for your needs, right? So these are I have already mentioned about some of the characteristics. So the one other characteristic is the range, right? So what is the range of values it can take care or deal with. Then the linearity, how linear it is. So if it is linear, it is more proportional. I mean, it is more predictable as well, and it is easy to compute. Then the response time, how fast the sensor is, how or how what is it sluggish, or is it very prompt to respond to some stimulus. Then stability and sensitivity I've already already talked about. Then comes the error with respect to the desired value or as compared to the benchmark value, and easiness of in replication. Then comes different environmental factors and economic factors before choosing the sensor, right? Is it a very bulky sensor, or is it does it get affected by humidity or corrosion? Or does it consume a lot of power? Some of the sensors are quite active, some are passive. So then we can have economic factors like cost and availability, reliability. Let us take an example of a temperature sensor again. So it's called resistance temperature detector, and they can be of different types. So one is of nickel type, the other is copper type, the other is the platinum type. Now the material, they affect the nature of the sensor, and of course the performance of the sensor also. So they affect several factors such as uh, the linearity, right, the response, the range of values that it can address. And yeah, so typically they have different ranges of operation, but these three attributes are very important for this resistance temperature detector. The higher the accuracy, obviously accuracy is very important, then linearity and repeatability. So so this is to represent the characteristics of the resistance of a RTD, of an RTD, right? So this expression is for the resistance as a function of the temperature that it is subjected to. So T is the temperature that it is subjected to, and alpha, beta, gamma are the temperature coefficients of resistance, and show how the resistance is sensitive to temperature. Right. So be using this alpha, the coefficient of these alpha, which are alpha, beta, and gamma, they say how the resistance is affected by the temperature. So R naught is the nominal resistance at 0 degrees Celsius, and RT is the temperature at is the resistance at capital T temperature. Okay. So in this case, platinum is typically platinum is a very common type of RTD sensor because of the fact that it is linear, it is repeatable, and can be used over a wider range. Right? So you can see the characteristics, right? With increasing temperature, there is a linear response of the platinum sensor. So the output value, the ratio of the ratio of the resistance at temperature T and R naught resistance R naught, we can see the ratio keeps on increasing in a linear fashion for the platinum, but not so much for the cases of copper and nickel. Okay, so they are not so predictable, and then there are and then it's easy to compute, and several other benefits are there. So this is one type of RTD sensor. It's called PT100. It's very, very common. In fact, I also have it. So 100 signifies the fact that the resistance R naught, that is the nominal resistance at 0 degrees Celsius, is of 100 ohm value. Okay? And yeah, so this is how it looks like. Now coming to data sheet. Data sheets are very important, especially when you are trying to buy a sensor for yourself. Right? So how do you do that? You have to look at several attributes that I have already talked about, and then this specifies. So these data sheets specify the characteristics of the sensor. So the different manufacturers, they provide data sheets of their products that they have manufactured, and then you can choose the right sensor for your needs. Right? So let's say for this, the data sheet is that for of an RTD, and it says that it is of type platinum type, thin film platinum RTD, and different uh, nominal resistances at 0 degrees Celsius are possible. Right, the two types of sensors for under this category, and then we can have temperature range based on the material, the lead material that you're having, whether it's Teflon or fiberglass insulated. So based on that, you can have different temperature range that it can operate at. Right, and then there is this linearity. So how what is the deviation from the linear response? Right? So for smaller range of minus 40 degrees to 125 degrees Celsius, the deviation from the linear characteristics is quite less. But when you go to a higher range of operation of temperature from minus 75 degrees to plus 540 degrees Celsius, you can see the deviation is increasing to around plus minus 2%. The time constant is less than 0.5 seconds, which tells about the response time of the sensor. And there are, again, I have talked about stability as well, what it means and all, and insulation, resistance, and all these attributes. So using this, you can choose the right sensor for your needs. Now coming to another type of sensor called the ultrasonic sensor. The ultrasonic sensor is again a type of motion sensor or proximity sensor. Right? So they're used for measuring a distance or object motion. So while there is relative motion, or even in static conditions also. Okay, so they use ultrasound, that is sound of higher frequency, some that frequency which even humans cannot even hear, and to detect motion. Right? So they convert a reflected sound into corresponding electrical signal, and they also generate acoustic sounds based on the signal that are commanded by the that are commanded by the some intelligent device inside the um, inside the sensor. So there is an intelligent device which will give some signal in order to produce some acoustic signal, and this acoustic signal, when it returns back, will be interpreted as the distance based on the calculation of speed and time of travel. Yeah, the waves emitted, acoustic waves, or the ultrasound waves emitted are of more than 20 kilohertz and can go up to 40 kilohertz. So they receive echoes by obstacles if there are any. But if there are no obstacles, they won't receive any echo. And based on which they'll calculate the distance. The distance is typically they can measure in the range from 2 centimeter to 400 centimeter, or 2 centimeter to 4 meters. That is the range. So beyond which they will not be able to measure. So the accuracy is about zero point 0.3 centimeter, which is sufficient for applications of, let's say, robotic systems, or no, not high precision, but simple robotic systems, as well as in they can be useful in the automotive systems as well. So yeah, so we can also have a high sensitive module which can be used with microcontroller to integrate with motion circuits, right, with for robotic applications and other motion sensitive things. So they can also be used for safety applications as well. Okay, now we shall now move on to the actuators. So these hardware devices, they convert a controller command into a change in the physical parameter. Right? Uh, so that's what the actuators are mainly concerned about. So they usually change. The change is typically in mechanical terms, right? There is some actuation, so there is typically a force produced, so that there is some motion in the long eventually. So under certain cases, we can also have the light. Let's say that an LED blinking. That is also one type of actuator in which it receives the command of to glow. And then it lights out. It turns on the light. So that is also one actuation, or a switch getting turned on or turned off. So that is also an actuation. Right? So there is some motion, or maybe some activity involved, whether it's glowing a light, or whether it's turning on or off a switch. So, by the way, the actuator is also a transducer because it changes from one type of physical quantity into another alternative form. But obviously, by now you might have realized that actuators and sensors are quite distinct. Okay, so they are typically actuated by by low-level command signals. So an amplifier can be required to provide the sufficient power to drive the actuator. So these are the internal mechanisms, an actuator in a generalized manner. So an actuator sensor as a feedback can also help to ensure whether the intended action has been taken by the actuator or not. So we'll come to that in just after within a short time. You might ask this question, that why do we have a sensor if the actuators and sensors are different? We'll come to that. Right? So let us start with the actuator. They receive a logical signal, and based on the logical signal, they will there will be some further signal processing and amplification if required, because they may not be in the proper manner acceptable, so they have to be fine-tuned and processed, and then they'll be fed to the mechanism of actuation. So this actuation mechanism can be through the electrical system, or maybe electromotor, or it can be hydraulic system or pneumatic system, or it can be a combination of them, electrical or hydraulic, or electrical pneumatic. or just an electrical system, and then they'll create that actuation in such a way that they'll be acting on a device which will do the job of actuating something, which will be fed. This actuation will be again fed to the plant, or rather to the it's called the process which is to be affected. Let's say that this is all connected to a valve, right? So the valve have to be moved, right? So in order to move, there will be a motion. In order to have motion, you need some let's say servo motor to rotate it at some speed. So for that, the servo motor has to draw current, right? So all these things have to be then for that, if it is of higher value, obviously typically it is of higher value, so you need an amplification for that. You need an amplifier to supply the amount of power that is required to, let's say, rotate the actuator. So this actuator will be, let's say, connected to this final actuating element. And then and the force will be provided by this mechanism, and the command obviously will be coming from here. Now I'll just now revert back to the actuator sensor. So this sensor will try to ensure whether the intended action is actually performed or not, right? So then based on that, maybe more corrective measures can be taken. Okay. So as I have already mentioned that they trigger some action based on the command from the microprocessor or microcontroller. So actuators are actually the part of the overall control system. Yeah, and their role is to facilitate the actuation process. So this is the loop of a control system. You start with the let's forget about the actuator for the time being. So this is the loop in which we want a desired set point, right? So let's say that this is a vehicle, and we want to achieve there's something called the adaptive cruise control, or okay, for those of you who are not very familiar with that, so let us stick to the fact that we want to have an output velocity of the vehicle, a desired output velocity. Let's let it be 50 kilometer per hour. And based on the controller and actuation and these processes, these activities, the process which happens to be the vehicle will exhibit some speed. So let's say that it's only 30 kilometer per hour. So then the sensor will feed this back, and based on the error, that this reference was 50 kilometer per hour and this is 30 kilometer per hour, and then based on the error, the control will react and it will give the suitable command which will be required to ensure that the vehicle indeed moves at 50 kilometer per hour. So how will that be possible? Let's say that we want to open the airflow to a higher extent inside the vehicle, inside the engine, so that the engine will receive more air, and then in response to which there will be more combustion, and then the vehicle will move at a higher, eventually at a higher speed. So the actuator will be responsible for increasing the opening of the valve to some extent. So by the way, actuator don't just open valves, they do other things as well, but this will be the manipulated variable. So this will actually be instrumental in the controlling the state of that plant. So in this case, I was just talking about the vehicle, but it can be other entity as well. And then this will get affected, and then it will change the output of the system. It might so happen that it might get affected by the disturbances as well. Okay. And then this will be again reported by the sensor. And the moment there is a discrepancy between the set point and the observed, based on the error, then again the controller will again correct itself and give the right amount of command to the actuator through the control signal. The actuator will give a higher value or higher or lower value as this situation, and then the process will react accordingly. Okay. So there are different types of actuators. We can have electrical actuators, we can have hydraulic actuators, we can have pneumatic actuators, right? So under electrical actuators, we can have electrical motors or solenoids. Okay. So under electrical motors, again, we can have DC servo motors or AC motors or stepper motors. They are very, very common actuators. Then we can also have hydraulic actuators, use hydraulic fluid to amplify the controller command signal. So they can be used in brakes of vehicles, let's say trucks. Okay, so to actuate that amount of force, but they can be they're used in other places as well. Then we can have pneumatic actuators. So they use this compressed air as the driving force. Okay, so let us look more closely uh, at the simple but important actuator, the solenoid, as a case example. Okay, so solenoids. So it consists of a coil and a soft iron, right? So it operates based on the principle of electromagnetic electromagnetic theory. And what happens is there is a coil that typically wrapped around a soft iron core, and there are electric lines of forces, electromagnetic lines of forces, which will be, if there is a soft iron core, they'll be more concentrated through the soft iron core, and then they'll cause this lines of force to result in either push or pull pull activities if in the presence of ferromagnetic elements. Okay, so as I said, that they are capable of exerting a force thanks to the electromagnetic forces. So this is what is happening. This is a typical circuit. The circuit is such that you have this is a relay actually. Okay, and let's say that this is a circuit, and this is the output circuit. These are the terminals of the output circuit. And let us look at the rest of the circuit, right? So this is one circuit. This is a metal. These two are insulators, and let us walk through the circuit. So this will move from here all the way here and all the way, but here there is a disruption because there is lack of contact between there is lack of contact between the relay contacts, right? So and then again it is connected to one of the terminals. So in this case we can see that there is clearly there is a gap, so the circuit is incomplete, right? There is no, possibly we cannot have any flow of current between there because there is a gap here. But the internal or rather the circuit, the input circuit of the relay will have a coil here, so which if we pass a control signal and pass current through it, there will be lines of forces, magnetic lines of forces passing through this soft iron core, and because of the soft iron cores they'll be more concentrated here, and they might result in push or pull operation based on the way these solenoids are, whether it's south pole or north pole, or whether based on the polarity of the this is basically this is the electromagnet, and this will cause the attraction or repelling, or it will attract or repel. So in this case, if it attracts, then this will get pushed or pulled, and then the relay contact will be made, and the moment relay contact will be made, we'll have a complete circuit. If the output circuit is again completed, the output terminals are connected to a voltage source as well as a load. So if the load voltage source become directly in contact with this, get directly in contact because of this closing of the relay contacts, then it will result in a closed circuit and current will flow. And suddenly you can see that the voltage, earlier it was zero, the zero voltage was applied to the external output circuit, but now after the closure of this relay, suddenly it will become V0 voltage, which is applied, voltage. So this is the outside circuit, external circuit. This is the input circuit, which is through which we control. Okay. So typically this is how they look like, solenoids. It's just the way the manufacturers package them. Okay, and there are several uses such as safety covers. So they're basically electromagnets. So either they can push or pull. So if they pull, they'll keep to ends latched, just like we can have here in relay contacts. They'll ensure that the covers are close together, so that they can be safe while some machine is in operation or not. So to lock or unlock doors in a car, especially for the keyless automatic entry, when the remote is pressed, so they'll just, based on the solenoid, they'll just get the internal circuit will get triggered, and then you establish a connection. So it's very simple. It's either you attract it, or you repel it, or you just de-energize it. Then automatically, this, if there is a spring, it will just go into no contact mode. And yeah, so we can also use it for opening and closing of valves in the industrial processes. And yeah, so or in a tape player, record head to press against by pushing or pulling, and such activities. Okay, with this I'd like to conclude. Thank you very much.